So, we are in the last module of this course, intelligent control, module 4. The broad topic is fuzzy control. In the first class we discussed we took a look at the various fuzzy control schemes that are prevailing in the literature. Today we will be now we will be discussing all those schemes in depth. So, today we will be discussing on Mamdani type fuzzy logic controller and parameter optimization. So, basic architecture of a Mamdani type fuzzy logic controller we have already discussed in the previous in the second module on fuzzy logic about this, but we will just revisit that. The issue always with Mamdani type is that how do we optimize the parameters. We will very briefly discuss what is genetic algorithm, fuzzy logic controller for a single link manipulator. Now, univariate marginal distribution algorithm, this is another genetic algorithm, evolutionary computation approach for optimization. We will compare both this genetic algorithm, simple genetic algorithm and univariate marginal distribution algorithm in a generic example of a robot arm control. So, how does fuzzy logic controller work? Define the control objectives and criteria. Given a system, we have to say what are the control objectives, what are the parameters of system to be controlled, what kind of response is needed, what are the possible system failure modes. Now, for this system, determine the input and output relationship and choose a minimum number of variables for input to the fuzzy logic controller engine, typically error and rate of change of error for fuzzy PID controller. I hope that you remember in our last class in fuzzy logic, sorry, not in the last class, in previous one of our previous classes, we have discussed that how a PI or PID type of controller can be represented in terms of error and change in error, or they are function of error and change in error. Using the rule based structure of a fuzzy logic controller, break the control problem down into a series of if x and y then z rules that define the desired controller output response for a given system input conditions. Create fuzzy logic controller membership functions that define the meaning or values, the linguistic values of input output terms used in the rules, because a fuzzy logic controller receives the crisp input, but the computation is through linguistic variables, and after that the output is again crisp, because the system which is out there is processing crisp input and crisp output. The next is test the system, evaluate the results, tune the rules and membership function and continuously simulate until satisfactory results are obtained. Okay. So, complete architecture of a fuzzy logic controller, this is our plant or process. You have sensors, then you get the plant feedback through sensors which are converted to fuzzy linguistic variables, which is known as fuzzification. Then that goes to the rule base and then inference mechanism, and then information mechanism actuates the control signal in fuzzy variable, which is done which is converted to crisp values through defuzzification, and then the driver or actuator gives to the control signal to the actual process. So, this is our architecture. So, you see that normally if say for example, this is my error and this is my membership function mu and the maximum value is 1. So, you see that if my change in error, this is in unit, So, we can define here it is shown that this is positive very large, positive large. So, this is just giving an idea what is PVL is positive very large. Similarly, NVL is negative very large. So, you see that these are the way, these are the linguistic values, negative large, negative medium, negative small, 0. So, the 0 is around the value 0, positive small, positive medium, positive large, positive very large. So, this way you see that in this case the variable E, the error, has been fuzzy partitioned into 9 fuzzy linguistic variables from negative very large to positive very large. So, once you fuzzify a crisp variable, then we are almost very clear about the rule base. For example, here a rule base for fuzzy PID controller has 2 input variables, error and change in error. If each input variable is fuzzy partitioned as negative very large, negative medium and so forth until positive very large respectively, then the fuzzy rule base is the fuzzy rule base is, you see that how do we found out the rule. So, this is my error and this is my change in error. So, what I am saying is that error is negative very large, negative large until positive very large, and change in error is this D is a differential term. So, that is also negative very large, negative medium. D simply refers here to change in error. Okay. So, that is also fuzzy partitioned into 9. So, 9 into 9, obviously the number of rules are 81. So, how do I do really? If I say error is negative very large and change in error is negative very large, then my control action should be negative very large. Okay. And we can take any other example. Let us say positive medium, my change in error, and error is 0. So, the action should be positive medium. Okay. So, this is where, so you see that all 81 rules are possible, maximum number of rules given 8 fuzzy partitioning zones in 2 variables, then 9 into 9 total 81 rules, means 81 combinations are possible. So, total is 81 rules. So, once rule is given, then given a situation, we see which are the rules, like if you look at here, given a situation all the things will not fire. For example, you see here if my crisp values are here, so only 2 rules will fire, 0 error and positive small. Okay. So, in that sense maximum time 2 rules fire, otherwise it all depends how you have fuzzified. I cannot say that only 2 rules will be firing. Also you can make rules only 1 rule, but at least 1 rule has to fire, otherwise your scheme is not right. So, you have to design in such a way at least 1 rule will fire, okay, given a situation, but in general more than 1 rule fires, but in general the fuzzy partitioning is done in such a way 2 rules fire. So, that is why you are seeing 2 rule, yes, rule 1 and rule 2. So, given this we find out given this rule, this is my crisp input, this rule 1 fires and gives, this is my control action, and similarly rule 2 fires and gives me the control action like this. So, then what we do is that is shaded portion is the control action, this is given by mean principle, and now we add these 2 shaded area and then we get this complete area, and this is my complete action, control action. How do I find out this is fuzzy control action, and this fuzzy control action is converted to the crisp control action using center of gravity method. Okay. So, this we have already discussed the center of gravity method. So, in general now I would like to turn your attention why we are doing fuzzy logic controller. We are doing because fuzzy logic controller was conceived as a better method for sorting and handling data. It has proved to be an excellent choice for many control system applications, since it mimics human control logic. It can be built into anything from small handmade products to large computerized process control systems. Fuzzy based control has become highly competitive due to its better performance, high reliability, robustness, low power consumption and cheapness. The thinking process involved in fuzzy realm is not complex, it is simple, elegant, easy to apply. Fuzzy logic control is one of the methodologies for solving control system problem. It lends itself for implementation in systems ranging from simple small embedded microcontroller to large networked multi-channel PC or workstation based data acquisition and control system. It can be implemented in hardware, software or combination of both. Fuzzy control directly also can be implemented in fuzzy hardware, fuzzy chips. A fuzzy logic controller provides a simple way to arrive at a definite conclusion based upon vague, ambiguous, imprecise, noisy or missing input information. Fuzzy logic controller approach to control problems mimics how a person would make a decision at a much faster rate. It is inherently robust since it does not require precise noise free inputs. The output control is a smooth control function despite a wide range of input variations. Since the fuzzy logic controller processes user defined rules governing the target control system, it can be modified and tweaked easily to improve or alter the system performance drastically. New sensors can easily be incorporated into the system simply by generating appropriate governing rules. Fuzzy logic controller is not limited to a few input or outputs. It allows the sensor to be inexpensive and imprecise. It keeps the overall system cost effective and low complexity. Because of the rule based operation, any reasonable number of inputs can be processed and numerous outputs can be generated. Defining the rule becomes complex if too many inputs and outputs are chosen for a single implementation. It is better to break control system into smaller chunks and use several smaller fuzzy logic controller that can be distributed on the system. Fuzzy logic controller can be used to control nonlinear systems that would be difficult or impossible to model mathematically. This opens doors for control system designer that would normally be deemed infeasible for automation. Finally, fuzzy logic controller provides a different approach to control complex systems. This method focuses on what the system should do rather than trying to model how it works. One can concentrate on solving the problem rather than trying to model the system mathematically, if that is even possible. On the other hand, the fuzzy approach requires a sufficient expert knowledge for the formulation of rule base, the combination of the sets and defuzzification. The drawbacks of the Mamnani type of, so now we talked about fuzzy logic controller. It's we kind of found the positive aspects of fuzzy logic controller. Now we are only discussing now Mamnani type of fuzzy logic controller. The problem is that you have rule base and it is associated with many parameters, the membership parameters, and these membership parameters, because how many rules, how many fuzzy zone partitioning and all those things, and membership function, whether you can select, if you are selecting Gaussian membership function, then a Gaussian membership function is characterized by two parameters, one is the mean, another is the sigma. So the how do we optimize, because normally what the engineer does is that he kind of heuristically tunes these rules, but can there be a proper method of tuning? So normally the genetic algorithms are good technique to update these parameters, but this is only possible if we are doing offline simulation. that is the model that is being controlled, we have some kind of mathematical form. Okay. Sorry, the system that we are trying to control, we have a mathematical model for it. Then we can always design a fuzzy logic controller using Mamdani type, and we can optimize the parameters using genetic algorithm. So, normally what is done is that given a physical system, you take some approximate mathematical model and do offline simulation, optimize the parameters and take to the real time system, and there heuristically tune the parameters. Okay. So, GAs perform parallel search. What is GA? Now, GAs perform parallel search to find out optimal parameters, where each local search does either a hill climbing or a gradient search. So, a genetic algorithm, you see the first initial population means this is the this when I say initial population means in the case of control systems, solution random solution space of parameters. So, if I know every parameter has certain range, so in that range I create random numbers, then I take each solution set and then I take each parameter set and then evaluate the fitness. So, based on the fitness value, but in this case what is the fitness? Obviously the tracking error. Okay. So, if the tracking error is minimum in a specific case, that is in the top. So, similarly there are various so we reorganize or rearrange this population in terms of their fitness, and there are various methods for selection, and specifically for control system you are very comfortable simply doing proportional selection. Proportional selection means according to their fitness the selection is done. Okay. So, if I say I take the initial population say 100 and I say I will always select after every iteration only 30% of them. So, that means 30% of the top best candidates are selected, and from those candidates 30% okay, from this 100. So, I have 100, I categorize them according to their fitness value, and then 30% I take, and these 30% through crossover and mutations are again converted 100. I started with 100 solutions using fitness, evaluated through fitness. I did a selection in terms of proportional selection, 30% means 30 best out of 100 are taken, and through crossover and mutation I duplicate this 30 to 100 again. So, initial population was 100, we went through the evaluation process using a fitness cost function, then we did the selection okay, using the best values, and then using crossover mutation we again got 100. So, what is the stopping criteria? Stopping criteria is that how much tracking error I need. Okay. So, or normally we select a stopping criteria is that what is our what is the minimal requirement of our tracking error or root mean square of the tracking error or something like that, or you can always say also I do just 100 iterations or 1000 iterations. So, one of them, and then whatever stopping criteria you get the out of those solutions what is the best, you take that best and that is your the optimal solution. So, the now we will utilize this concept to control. We take a very simple example, it is better to learn a subject through simple example. So, again consider a single link manipulator, what you are seeing here, this is my link, this is a motor, and so I apply the control torque, and this is my angle theta. Okay. And this if I assume this theta is actually from this angle theta. So, this is this angle theta. So, then m l square theta double dot plus m g l sin theta is tau. Okay. So, m is 1 kg, L is 1 meter, g is 9.81 kg per meter square. So, it is desired that the link will follow. So, we are talking about how we implement for a robot manipulator a PD controller. It is desired that link will follow a desired trajectory x t equal to sin t. Okay. So, what we are saying that this will simply oscillate around its vertical position like this. The PD controller, tracking error is obviously sin t, the desired trajectory minus theta t. The PD controller tau equal to Kp plus Et plus Kd into E dot t. So, this is our PD controller. Okay. Kp into error plus the derivative gain into the differential of the error. Kp is the proportional gain and Kd is the derivative gain. Although parameter Kp and Kd are heuristically determined, the optimal values can be obtained using genetic algorithm. So, for certain purpose what we did that this is a multi objective function. We want to minimize the square error in the cost function in error as well as the change in error. Okay. And here also the total control effort, okay, the square, the quadratic function in error and quadratic function in change in error and quadratic function in the actuated control input. So, we want to minimize both. Okay. So, doing that running a genetic algorithm for this, we got the Kp value is 74 and Kd value is 3. Now, we will see that for the same robot manipulator also can be controlled using a feedback linearization. So, for this again the same manipulator m l square theta double dot plus m g l sin theta tau. It is desired that it will track sin t, again setting the error sin t minus theta t as the error. We get the derivative of error is cos t minus theta dot t, and the double derivative of E error is minus sin t minus theta double dot t. So, if I select a filter tracking error R t to be E dot t lambda E t, then I can write R dot t is E double dot t plus lambda E dot t, and this E double dot t can be written here minus sin t minus theta double dot t plus lambda E dot t. So, here this theta double dot t can be taken from here from this expression, okay, and which is tau minus mgl sin theta upon ml square theta is theta double dot. Okay. So, this is theta double dot minus lambda E dot is retained here minus sin t is retained here. So, this is my closed loop aerodynamics. This is my closed loop aerodynamics. So, to make it if I take the value of m equal to 1, L equal to 1, my final closed loop dynamic becomes this one r dot 2 r dot t is minus sin t plus lambda E dot t minus tau minus g sin theta. So, how do I select my control law tau such that this is stable? So, if the control law is selected, tau is minus sin t plus lambda E dot plus g sin theta plus k r, then the closed loop aerodynamics becomes r dot t is minus k r. So, this is stable if k is a positive constant. Okay. So, this is a very simple feedback linearization, because it is a nonlinear system. We selected tau, the control law, which is this one. This is the control law. Okay. If you select this control law, we are able to show that the closed loop error dynamics is given by R dot T is minus K R T. So, this is a stable dynamics. So, what we did is that we did a feedback linearization. Before that we did classical PD controller, and also using the earlier fuzzy controller also we implement a fuzzy controller. So, now let us see the performance. PD controller, what is the performance? Performance, you see that this is the solid line is my desired and the broken line is the actual. So, you see the tracking is not so good, which is natural because simple PD controller. So, and hence and the control actions are given here. Okay. And this is the most optimal performance of a PD controller, because we have optimized the parameter of Kp and Kd using genetic algorithm. Now, feedback, this is FBL is feedback linearization technique. So, using this controller you usually see that the tracking is very good, as well as the oscillation in the input torque is reduced here, and it is very smooth torque. Now, we have implemented a fuzzy logic controller with G optimization. Okay. So, using this, when we did, again the performance is good with the control actuation is also very smooth, just like feedback. Feedback linearization is the best achieves the very good controller. So, fuzzy logic controller, which was started with this G optimization, also provides a similar response. So, if I want to compare the comparative performance, you see that fuzzy controller, with the same, you can see that same control input effort, you see that this is comparative, because we are almost applying same control input 5.1, 5.1, 4.8 Newton meter. This is the root mean square control force. Okay. So, total control at every time. So, if I have UK, or if I say UT square into dt, I find out, and then average it, then take the root mean square. So, I get this control effort, and correspondingly you see that fuzzy controller has the order of error is 10 to the power minus 3, but PD controller has 10 to the power minus 2, and linear feedback controller has 10 to the power minus 4. So, fuzzy controller is almost equivalent to linearized feedback controller. We will now, of course, this is just an example using some simple example. The fuzzy logic controller performance also can be further improved. The univariate, we will now discuss about another evolutionary computation approach for optimization. The univariate marginal distribution algorithm, UMDA, estimates the distribution of gene frequencies using mean field approximation. Each string in the population is represented by a binary vector x. The algorithm generates new points according to following distribution. Okay. So, this is called mean field approximation. Okay. So, this is the distribution of a total string, and this is the individual bits in the string. So, the UMD algorithm, so it is a, so what is the meaning of this, that if x is a vector of x1, x2 and x3, okay, then Px is simply Px1, Px2, Px3. This is called mean field approximation in probability theory. Okay. So, probability joint distribution is computed simply multiplication of individual or marginal distribution. Okay. So, the step 1 set t equal to 1 and generate n binary strings randomly, okay, and these binary strings represent certain parameters. Step 2, select m less than n strings according to a selection method, normally proportional method. Step 3, compute the marginal frequencies, okay, for each one from the selected strings. Generate new endpoints according to this distribution which you have derived, okay, and set t equal to t plus 1. If the termination criteria are not met, go to step 2. So, the example I will say you, like let us say I have the string consists of 3 bits and I have such three such strings, then you can easily see the marginal frequency of 1 in the first bit is 1 upon 3 and marginal frequency of 1 in the second bit is 2 by 3 and marginal frequency of 1 in the third bit is 2 upon 3. So, obviously, the probability joint distribution of x 1 equal to 1, x 2 equal to 2 and x 3 equal to 1 is simply multiplication of this, which is 1 upon 3 into 2 upon 3 into 2 upon 3. You can easily see this is 4 upon 3 q or 27, 4 upon 27. So, how do we do it? New population generated according to this marginal frequency distribution. So, what I do in the next time when I generate here okay. So, I generate, so what I had say 10 strings, I did a selection and I pruned to 3 best and these 3 best are converted again to 10 number of population to 10 okay, to using this. So, what I do is that the first strings okay, they are generated I will generate a 1 with a probability 1 upon 3 okay, and with probability 1 upon 3 is 1 is selected and with probability 2 upon 3 0 is selected in this first string first bit, and second bit with the probability 2 upon 3 I select a 1 otherwise 0, and similarly third one with the probability 2 upon 3 I select 1 and with probability 1 upon 3 I select a 0. Okay. So, this is a UMDA, univariate marginal distribution algorithm. So, now we will show you in this particular lecture the application of this particular univariate marginal distribution algorithm to a robot arm control. The general approach to control a robot arm is to actuate a feed forward torque which is computed based on inverse dynamics model of the robot arm and a feedback torque that is computed using position and velocity feedback terms. The schematic diagram for such a control architecture is as follows. So, what you are seeing is here that given a robot arm, this is my robot manipulator. The normal approach to control a robot arm is that I have a inverse dynamics which gives me, given the desired trajectory, gives me what is the feed forward torque, and given the desired trajectory using the feedback actual output feedback, I have a PD controller and that actuator is tau feedback and this is the total tau, and the objective is that that the robot manipulator should follow the desired trajectory QD, that means Q should follow QD. This is a generic architecture for a robot manipulator, this is inversion, this is for stability. So, now you see that given if I assume that robot manipulator dynamics are not exactly known or there are uncertainties, what I can do is that I can learn inverse dynamics of a robot manipulator, okay. And I put this inverse dynamics here, and I can also design, instead of a PD controller, a fuzzy PD controller. So, now I am controlling the same system using a different approach, that is fuzzy logic control. So, what is inverse dynamics model? In the absence of dynamic and parametric uncertainties, the inverse model can be directly computed in terms of desired link position, velocity and acceleration using forward dynamics of the robot arm. So, this is very simple. In a general robot dynamics is m theta double dot c theta dot plus g is tau. So, all that I have to do is that if I know what is m l g, then given theta d, theta dot d and theta double dot d, I can compute what is tau. Okay. So, this is the best way to control the robot manipulator, because then this is a inverse dynamics. Okay. But unfortunate most of the time the parameters that we identify m, c and g, they may not be exact. Okay. However, the inherent uncertainties compel the control engineer to estimate the model using neural networks or fuzzy logic. The generic form of the inverse dynamics for a robot manipulator is thus given as tau is a function of q desired, velocity desired and acceleration desired. So, tau is the required torque, and position, velocity and acceleration are the link position, velocity and acceleration respectively. It is the fuzzy model of the inverse dynamics. So, you see that we talked about this model. First we will solve this one, how to derive a fuzzy logic, fuzzy inverse dynamics of a given robot manipulator. So, the generic form of a fuzzy model is given as, if x 1 is a 1, x 2 is a 2 and x n is a n, then y is b, where x I is the fuzzy input variable for the model, a I is the fuzzy attribute of x I and y is the fuzzy output and b is the fuzzy attribute of a y. For a single link manipulator, if I take m l square theta double dot plus m g l cos theta is tau, the fuzzy inverse dynamics model maps two fuzzy input variables q, sorry, this is not q, this is theta and theta double dot, okay, to one fuzzy output variable. Sometimes we represent this angular position and angular velocity and acceleration either in terms of theta or q. So we have two variables here, theta and theta double dot, because we know now that torque does not depend on the other variable, which is theta dot. So, how many variables then this the inverse model is dependent on? In this particular example, two input variables. So, each input variable is fuzzy partitioned into 6 regions: negative big, negative medium, negative small, positive medium and positive big. So, once you have two input variables and each input variable is fuzzy partitioned into 6 zones, then obviously we have the rule base that will consist of maximum possible 36 rules to describe the dynamics. For simplicity, we assume that the output fuzzy variables is a fuzzy singleton. Okay. So, it is just a simple fuzzy singleton means it is like this. Okay. This is called fuzzy singleton. Okay. But if the moment I represent, so then this is triangular membership, it can be Gaussian membership, but singleton means it has a single value. Okay. So, this is the x 1 whatever my output is. Okay. So, So, this is fuzzy singleton. The output of the fuzzy model is computed using center of gravity method, which we have already discussed, where R is the index for a rule, R is the small r is the index of a rule, capital R is the total number of rules, and mu r here is minimum of all these fuzzy index, that is a 1 of x 1, a 2 of x 2, n of x n. Okay. So, when I fuzzify, because given crisp values x 1, x 2, x n, their corresponding fuzzy values or fuzzy memberships are computed using the defined fuzzy membership function a 1, a 2 and a n. So, fuzzy parameters optimization. So, we saw that if I am trying to control a single link robot manipulator, I have to design two things. One is inverse dynamic model and another is a fuzzy PD controller. We are now doing fuzzy inverse dynamics. So, in this we saw that the torque, actuating torque, is a function of two variables, which is angular position and angular acceleration. The missing element is angular velocity. So, this two input fuzzy partitions into each one input is fuzzy partitioned into 6 variables, 6 linguistic variables, then we have 36 rules. And if I say that each membership function is a Gaussian membership function, which we have actually taken in this case, then each membership function is characterized by two parameters. One is mean, any Gaussian is by mean as well as the variance sigma. So, the inverse dynamics of a single link manipulator is described by two input variable and one output variable. Each input variable is fuzzy partitioned into 6 regions, and each region is characterized by two parameters, mean and variance, because of Gaussian membership function. So, the total number of parameters in the input space are 24, because I have 6 partition in the first input variable, another 6 partition in the second input variable, and each input each linguistic variable is characterized by 2. So, 6 plus 6 is 12 into 2 is 24, and there are total number of 36 rules. So, each rule is associated with one fuzzy singleton. So, that is 36 parameters, means if x 1 is a 1, x 2 is a 2, then y is a specific value, y is 10 unit, y is 20 unit, y is 40 unit, like that. Singleton value means it is not it is a precise value. So, there are 36 singleton parameters in the output space, one for each of the 36 rules. Thus, fuzzy inverse model consists of 60 parameters, 24 plus 36. Since the output is a nonlinear function in terms of these 60 parameters, the resulting nonlinear optimization problem is a good candidate within the evolutionary computation approach. So, what we will do is that we will now use simple genetic algorithm as well as UMDA, univariate marginal distribution algorithm, to learn this inverse dynamics, and we will compare which is doing better, because we have learned just two. So, the fuzzy inverse model parameters are optimized using both simple genetic algorithm and univariate marginal distribution algorithm. In simple genetic algorithm and univariate marginal distribution algorithm, each parameter is represented by a binary string that consists of 8 bits, and we have 60 parameters. So, 60 into 8 is 480 bits. So, that is, if I have a string in the population, each string consists of like that. So, 480 bits, and out of that 8 bits represent 1 parameters, and total number of 480 bits will represent 60 parameters, and initially the population size was kept at 1000. Okay. So, in simple genetic algorithm, the proportional selection is adopted, multi-point crossover is done, the mutation rate is kept at 0.01. Whereas, in univariate marginal distribution algorithm, 20% of the population are selected according to fitness. The univariate frequency of each bit is computed over the selected strings and a new population is generated accordingly. Okay. So, data for the inverse dynamics are generated using two following position trajectories. We took in one case desired trajectory to be cos 3 t, another case the desired trajectory q is 1 upon 3 cos t plus cos 2 t plus cos 3 t, and using this two trajectory we generated 500 data points, and both and for all these 500 data points we every step we took a parameter set and we computed the output and we matched whether given these values we can find out what is tau, right. And using SGA and UMDA, both SGA and simple genetic algorithm and univariate marginal distribution algorithm are evolved for 100 generations, okay, evolved for 100 generations, and the cost function is always evaluated for these 500 data points. Okay. So, if you see that the learning of UMDA, which is the solid line, and simple genetic algorithm, which is the broken line, you will see that error convergence in parametric evolution using univariate marginal distribution algorithm and simple genetic algorithm while modeling the inverse dynamics we are showing here, and the conclusion is UMDA univariate marginal distribution algorithm is faster than simple genetic algorithm. The interesting point is that this univariate marginal distribution algorithm is actually a very simplified form of probabilistic approach, purely probabilistic approach to evolve the solution space. The fuzzy inverse model using simple genetic algorithm, now we will test. Okay. So, the accuracy of the predicted model is tested by comparing with the desired torque corresponding to two different trajectories. So, what you are seeing is that this first trajectory what you are seeing corresponds, this is the desired torque, okay. This is the torque, output torque tau, okay, and the desired torque, and this is your the given trajectories. So, the if you see that the desired torque at different instances along the trajectory cos 3 t is this one, the desired torque, and SGA has is estimating the values like this. You see that this is SGA estimation, this is SGA estimation. So, you see it is not so accurate. Similarly, the second trajectory corresponding to second trajectory, the tau is computed like this value, whereas the predicted through inverse model is. So, there is certainly a discrepancy. This model learning is not good, but when you shift to univariate marginal distribution algorithm, you can check that the prediction is much better here using univariate marginal distribution. Here also the prediction is much better. Okay. So, for this first trajectory cos 3 t, and second trajectory is the summation of three different trajectories. So, the figures clearly show that univariate marginal distribution algorithm does better as compared to simple genetic algorithm. It is not that it is as a blanket statement, you know, even we are only considering genetic algorithm, simple genetic algorithm, but there are also very advanced genetic algorithms which may also do better than UMDA. So, the feedback, so we showed until now what is a inverse dynamic, fuzzy inverse dynamic model. Now, we will be talking about feedback fuzzy PD controller. The generic form of a rule in a fuzzy logic controller is again the same. If x1 is a1, x2 is a2 and xn is an, then the control action tau fb is b. The final control action is computed using center of gravity method. In case of a single link manipulator, two input variables are link position and link velocity and are fuzzy partitioned in 6 regions as negative big, negative medium, negative small, positive medium and positive big. So, also the only control variable is fuzzy partitioned into 8 regions: negative critical, negative big, negative medium, negative small, negative positive small, positive medium, positive big and positive critical. So, each fuzzy variables is represented by 2 parameters taking Gaussian membership function, its mean and variance. Thus, we have 40 variables. However, by fixing means of some fuzzy attributes such as negative small and positive small at 0, we reduce the parameter size to 30. So, you have to do little, because you are very sure you can fix certain parameters and then you reduce those parameters to 30. As before, each parameter is represented by 8 bits. So, naturally each string is now consisting of 240 bits. Okay. So, now you see that error convergence in parametric evolution using UMDA and SGA while designing fuzzy PD controller is that UMDA is pretty fast compared to simple genetic algorithm. Okay. So, finally, we first designed 2 aspects separately. Now, we will put both of them together and then we will design a robot arm control using both inverse dynamic and PD controller. Okay. So, if we do that, which we proposed earlier, you see that the robot arm control is simulated using fuzzy UMDA inverse dynamics and fuzzy UMDA PD controller, since UMDA performs better than SGA. In the first case, we used exact inverse dynamics along with fuzzy PD controller for a set point tracking. Then we assumed 20% model uncertainties in the actual model and the control scheme was implemented using fuzzy PD controller and a conventional PD controller. The results show that FLC is robust to parametric uncertainties. You see. So, in the beginning you see that this solid line, which is this one, this particular one. Okay. So, this solid line represents when we have the model is exact, for which we have derived what is the fuzzy inverse model, and we have derived what is the a fuzzy controller. Now, we introduced 20% model uncertainties, this one, and doing the model uncertainties we again are running on the same fuzzy logic controller which we derived for the exact model. Now, we took the 20% uncertainties in the parameters, we introduced that arbitrarily randomly, and then we saw the controller performance has not degraded, the second one, which one you are seeing this. But if you do simple the PD controller with the classical PD controller and assume the 20% model uncertainties, obviously due to model uncertainties you cannot go to the exact set point. So, this is your set point, desired set point. So, there is an error between the actual set point and desired set point. So, desired set point is 1 radian, which is this is. So, what we are saying that set point response FLC without model uncertainty is the first one, and this is my third one. So, FLC with model uncertainties does very nicely, and PD with model uncertainties you see that it has some error. So, So, finally, in this lecture following topics have been covered. We covered first of all what is Mamdani type of fuzzy logic controller, then parameter optimization using simple genetic algorithm and UMDA. We demonstrated that how these two optimization schemes work for robot arm control, but we give a caution here that adaptive fuzzy logic control is possible only if the offline simulation can be carried out. So, today we gave you some idea about that how do we do parameter optimization of fuzzy logic controller. In the next class, which will be interesting for you, for which we will show you how to generate rules from actual CRISP data in a manner that the fuzzy logic controller is stable. Here we are optimizing, and as long as our performance criteria is meeting, then we say okay, system is stable, but there is no ready made, we do not actually generate rules such that system is stable. So, next fuzzy logic controller, the type that we will be describing how to generate rule base using stability concept. Thank you.